I jo mateixa, que hauria de ser aquí al principi, que actuo com a presidenta i que soc projecte xarx de la Universitat del Camp de Barcelona. Bé, el que vulguis.
Okay, thank you very much and good morning everyone. For the next 50 minutes I will be presenting my thesis dissertation, which is entitled Cyclization Reactions for the Functionalization of Fullerenes, Experimental and Theoretical Studies. And I will give an overview of the works that I have been developing over the last 4 years under the supervision of Professor Ana Blancs, Professor Miquel Solà, and Gustavo Thiago. We are part of the Democrat Group, an interdisciplinary team of researchers working at the Institut de Química Computacional y Catàlisis, which is in turn established here at the Universitat de Girona. This slide shows an outline of the content I will be explaining today. I will first start with an introduction covering some essential aspects of the topics that have been developed during the thesis. Then I will go through the general objectives. In the third part, I will discuss the main results obtained during this thesis. This chapter is, as you can see here, divided in this part is divided in 4 chapters, as you can see here, and then after the discussion of the results, I will finish with a set of conclusions. I would like to clarify at this point that the manuscript of the thesis has an additional chapter 7 that will not be discussed today because of time constraints. Okay, so let's start with the introduction. I wanted to start this presentation talking about carbon. As most of the audience here may already know, carbon is element number 6 of the periodic table and can present itself in many different allotropic forms. For more than 7,000 years, humanity only knew 2 forms of carbon, graphite and diamond. But over the last 4 decades, many other carbon allotropes have been discovered and investigated, including fullerenes, carbon nanotubes, graphene, and the very recently discovered cyclo-18 carbon. All these allotropes of carbon have their particular structures and physicochemical properties, and my thesis has focused on fullerenes, who are the main characters of the story I am going to tell today. Okay, so fullerenes are considered the third allotropic form of carbon. They are defined as a group of hollow polyhedral molecules with a cage-like structure, showing carbon atoms at the vertices, CC bonds at the edges, and 5 and 6 member rings forming hexagonal and pentagonal faces. Every fullerene must have an even number of carbon atoms that are organized in exactly 12 pentagons and a variable number of hexagons. In general, fullerenes fulfill the so-called isolated pentagon rule, which establishes that the most stable fullerenes are those that have all pentagons surrounded by hexagons. Fullerenes are artificially produced from graphite rods in an arc discharge reactor that produces this black soot that is constituted by a complex mixture of carbon-based species that, upon extraction and different chromatographic techniques, ultimately deliver fullerenes in their pure form. This molecule here is C60. It was the first fullerene to be discovered back in 1985 by these 3 scientists, Protos, Molly, and Pearl, who, by the way, deserved the Nobel Prize in Chemistry 11 years later for their discovery. Fluorine is of course constituted of 60 carbon atoms organized in 12 pentagons and 20 hexagons. It's the smallest fluorine to obey the isolated pentagon rule and has a highly symmetrical shape of a truncated icosahedron. In simpler words, C60 has the exact shape of a football. Because of its high symmetry, C60 has only two kinds of non-equivalent carbon-carbon bonds. The so-called 6-6 bonds are those found between two hexagons and are considered to have a double bond character, and by contrast, 5-6 bonds are those found between an hexagon and a pentagon and are considered to have a single bond character. C60 is by far the most abundant fluorine in soot after arc discharge, and for this reason, it has been the most studied fluorine by synthetic chemists and material scientists for almost 4 decades. Okay, fluorines and C60 are not only interesting molecules because of their beauty and their fascinating spherical shape, they also possess a series of photophysical and electrochemical properties that make fluorines very interesting molecules for their potential application in a variety of fields ranging from material science to biology. By far, the most developed of these potential applications is the use of fluorines in next generation photovoltaics. In fact, C60 and its derivatives are common anti-materials in organic and perovskite solar cells. Some studies have also suggested the use of fluorines in medicine as antiviral, antibacterial, antioxidant, or anti-cancer agents, but the truth in this case is that we are still very far from a fluorine-based drug with realistic clinical potential. Finally, I would like to highlight that a particular family of fluorines, the so-called endohedral metallofluorines, have been successfully used in the field of diagnosis as MRI contrast agents. Okay, unfortunately, fluorines themselves are not useful molecules. In order to become useful, they need to be functionalized. But luckily, in this regard, C60 has a reactivity that is analogous to that of electron-deficient molecules. It is for this reason that over the last 35 years since its discovery, a large number of chemical reactions have developed to modify the structure of the fluorine gates. In fact, nowadays, almost every functional group can be attached to the surface of C60 by properly choosing a synthetic strategy. Cyclization reactions like cyclopropanations, 3+2, 2+2, or 4+2 cycloadditions are often the method of choice when it comes to fluorine functionalization. It is very well established that these cyclization reactions occur selectively at the 6-6 bonds of C60 because of their double bond character. C60 can also participate in a large variety of transition metal-mediated annulation reactions like CH functionalization reactions or transition metal-mediated radical reactions. However, today I want to focus on a particular example of this class of reactions, which are the transition metal-promoted 2+2+2 cycloaddition reactions. Since this specific process constitutes the central core of the works that I have developed during my thesis, I will take some slides to comment specifically on this reaction. So let's take a closer look. In a few words, the transition metal promoted or catalyzed 2+2+2 cycloaddition reaction is a process in which 3 unsaturated molecules couple to form a new 6-member ring. The most common example of this reaction is the so-called acetylene cyclogenization, in which 3 alkynes participate in the reaction to form a new benzene ring. The reaction performs very well in its intermolecular form, starting from 3 disconnected substrates, but also more complex tether molecules can be used in the reaction, giving rise to the partially and totally intramolecular variation of the reaction. It is established that almost every transition metal can promote this reaction, but for today, I am going to focus only on rhodium complexes. This reaction is of course not limited to the use of alkynes, and in fact, many other unsaturated molecules can participate effectively in the reaction. The versatility of the 2+2+2 cycloaddition reaction is clearly exemplified by some examples reported by our research group. So in this regard, over the last 15 years, we have reported many examples of these transformations employing different rhodium-1 complexes as the catalyst and different unsaturated substrates like alkynes, nitriles, alkenes, or allenes as the starting unsaturated materials. As a result of this reaction, also very diversified carbon heterocyclic molecules can be formed, like benzene rings, cyclohexadiene or cyclohexene rings, and also heterocyclic compounds like pyridines. Okay, so coming back to fluorines, 2 plus 2 plus 2 cycloaddition reactions can be used to synthesize cyclohexadiene fused fluorine derivatives starting from C60 and two alkynes. These cyclohexadiene derivatives of C60, this molecule here, are very interesting molecules from the synthetic point of view because these molecules rearrange in order to provide these compounds here, known as bisfluoride, that exhibit an 8-membered hole at the surface of the fluorine. This hole can be chemically expanded to the point of allowing the encapsulation of small atoms and molecules. And moreover, the hole in the fluorine can be chemically sutured, again, allowing the selective synthesis of endohedral fluorines. This synthetic strategy is commonly known in the field as molecular surgery and has been extensively used over the last 2 decades to selectively encapsulate small atoms and molecules in the cavity of C60 from helium to very recently methane. Okay, to the best of our knowledge, at the very beginning of my thesis, only 2 previous works reported the 2 plus 2 plus 2 cyclohexadiene reaction of C60 and alkynes. As you can see in the slide, both examples require the use of a stoichiometric amount, even also the lack of an efficient and catalytic methodology to access these kind of molecules, and also given the proven ability of these rhodium-1 complexes to promote their reaction with a wide variety of unsaturated molecules, we anticipated that an improved version of this reaction could be developed by using rhodium-1 complexes as a catalyst. And this leads to the objectives of my work. So based on this precedent, we set the first general objective of my doctoral thesis, which was to study the rhodium-1 catalyzed 2 plus 2 plus 2 cyclohexadiene reaction of fluorines and alkyne. This general objective is divided into 3 smaller ones. First, to study computationally the process, then to develop a synthetic protocol based on rhodium catalysis to prepare cyclohexadiene fused C60 derivatives, and then to incorporate our newly synthesized compounds in photovoltaic devices. In an attempt to expand the scope of our developed synthetic methodology, we set the second objective of my thesis, which was to study the rhodium catalyzed 2 plus 2 plus 2 cyclohexadiene reactions of fluorines and 1,5-bisalines. Again, this objective is divided in 2. The first one was to develop a synthetic protocol for the 2 plus 2 plus 2 cyclohexadiene reaction between 1,5-bisalines and simple alkenes, and as a second objective, of course, to apply this synthetic protocol to functionalize fluorines. Okay, so I'm going to move now to the third part of the presentation, in which I'm going to highlight the most relevant results obtained during the thesis. In chapter 3, which is the first of the results and discussion, I am going to discuss on the a computational study on the intermolecular 2 plus 2 cyclohexadiene reaction of acetylene and C60 catalyzed by Wilkinson complex. Okay, so at the very beginning of my doctoral thesis, we wanted to obtain preliminary information on this process here, which is no other than the rhodium-1 catalyzed 2 plus 2 plus 2 cyclohexadiene reaction between C60 and 2 alkynes to deliver a fluorine-fused cyclohexadiene-fused fluorine derivatives. At this point, we wanted to answer 2 questions. First, we wanted to know what is the specific mechanism of this reaction. And then, based on this mechanism, we wanted to know if this is a feasible process. In other words, we wanted to know if rhodium-1 complexes can behave as efficient catalysts to promote this chemical reaction. The answer to these questions was provided by computational chemistry. Okay, so to perform a computational study, first we need is a reaction model. We chose, of course, C60 as the model fluorine, acetylene as the model alkyne, because in fact acetylene is the simplest possible alkyne. And as a model catalyst, we chose this neutral rhodium-1 complex, commonly known as Wilkinson's complex, because it has been widely used in related processes. We wanted to evaluate all mechanistic steps from reactants to this product by considering 2 possible reaction pathways. In path A, the initial oxidative coupling takes place between 2 acetylene molecules, and then insertion of C60 and reductive elimination ultimately delivers the cycloxylene derivatives. By contrast, in path B, the initial oxidative coupling takes place between an acetylene molecule and C60, and then it is the insertion of a second acetylene molecule and reductive elimination what delivers the same product. Regarding the computational method, all optimization and frequency calculations were computed at the B3 level of theory using a double zeta gaseous set and pseudo potential for rhodium. The energies were improved with single point energy calculations at the M06L level of theory using, in this case, a triple zeta gaseous set and again a pseudo potential for rhodium. All calculations were performed in the gas phase, but for the most feasible pathway, we computed single point energy calculations with toluene as the model solvent in order to confirm the negligible effect in the reaction barriers of a non-polar solvent. Finally, all computational calculations incorporated D3 Grimes dispersion corrections with the original damping function. Okay, so we performed our computational study and concluded that the mechanism proceeds as it follows. Okay, first step in the reaction is activation of the catalyst by substitution of one phosphine ligand by one acetylene molecule. This process delivers intermediate A2, which is actually the one that enters the catalytic cycle. This intermediate A2 coordinates to a second acetylene molecule, and then by interconversion into A3' and an oxidative coupling mechanism, this rhodocyclopentadiene intermediate A4 is formed. For the specific case of path A, the oxidative coupling step was found to be rate determining with an energetic span of 22.4 kcal per mole. Okay, by contrast, in path B, intermediate A2 coordinates to C60 instead of a second acetylene molecule, and then again by an oxidative coupling mechanism that is selective for a 6-6 bond of C60. This process delivers intermediate B4, which is a rhodocyclopentane intermediate. The energy barrier for path B is 21.0 kcal per mole, and as you can see in the slide, for the oxidative coupling step, the Gibbs energy profile of path B and path A are very similar. Okay, after the oxidative coupling step in path A, this intermediate A4 releases one phosphine ligand and coordinates to C60 to form this intermediate A6, and then by an insertion mechanism that is again selective for a 6-6 bond of C60, this intermediate A7, which is a rhodocyclopentadiene intermediate, is formed. In path B, intermediate B4 coordinates to an acetylene molecule, releases one phosphine, and again an insertion mechanism leads to the same intermediate A7. Interestingly, for path B, this insertion step was found to be rate determining with an energetic span of 26.1 kcal per mole. So comparing both reaction barriers for path A and path B, we can easily infer that path A is favored over path B. As you have seen in the previous slides, path A and path B merge in intermediate A7, and all subsequent reaction steps are coincident until the end of the catalytic cycle. So this intermediate A7 experiences a reductive elimination, delivering this cycloxylene intermediate A8, and then release of the reaction product, and A2 again by the entrance of another acetylene molecule ultimately closes the catalytic cycle. Overall, the 2+2+2 cyclation reaction between two acetylene molecules and C60 catalyzed by Wilkinson's complex releases 51.6 kcal per mole and has an energetic span of 22.4 kcal per mole, corresponding to the oxidative coupling step in path A. Okay, so next step in this project was to evaluate the chemoselectivity of the reaction, which means to assess at which extent insertion of C60 and subsequent reductive elimination can compete with the insertion of a third acetylene molecule and consequent formation of a benzene. This is the so-called cyclotrimerization pathway. So to do so, we computed the acetylene cyclotrimerization pathway at the same level of theory and compare it with the reaction with C60. As you can see in the slide, the acetylene cyclotrimerization pathway is clearly favored both thermodynamically and kinetically. Indeed, After the coordination of a third acetylene molecule, the reaction barriers are almost negligible and the process is much more exergonic. So as a conclusion of this third chapter, we have shown that the 2+2+2 cycloaddition reaction between acetylene and C60 catalyzed by Williams complex is indeed a feasible process, but it has to compete with a much more favorable cyclotrimerization pathway. This is something that we had to take into account in further experimental studies because most of the efforts in this regard were directed to switch this chemoselectivity. Okay, so after we finished our computational study, we decided to move to the synthetic lab and continue studying the reaction, but this time by experimental means. This is basically what I'm going to explain in chapter 4. Okay, in first attempts, we reacted C60 with this sulfonamide tethered diene as the alkyne containing reaction partner, either in the presence of catalytic or sedimentary amounts of the Wilkinson's complex. If you remember from the previous chapter, this is the same complex that was used in the computational study. Unfortunately, under these reaction conditions, C60 did not react with the diene and we were not able to isolate our desired cyclohexadiene derivative. In turn, we obtained full recovery of unreacted C60 and detected the formation of this cyclotrimerization homocoupling product that results from the reaction of the diene reacting with itself. In fact, this outcome of the reaction was not unexpected because if you remember from the previous chapter, we had already anticipated computationally that for this specific catalytic system, the cyclotrimerization pathway was favored over the reaction with C60. So our objective at this point of our investigations was to go from this situation to this one. Or in other words, we had to come up with rhodium-1 complex that is able to catalyze the reaction, but this time selectively for C60. So with this in mind, we turn our attention to cationic rhodium phosphine complexes. We were particularly interested in this kind of rhodium complexes because they had been used previously by our group and other groups in the 2+2+2 cycloaddition reaction of dienes and electron-deficient alkenes that can be considered somehow analogous to C60. So with this idea in mind and after some experimentation, we found out that heating a mixture of C60 and the same diene in the presence of a 10% molar mixture of this cationic rhodium-1 complex and using binap as a ligand led to the isolation of a dark brown solid that was expected to be, of course, this compound, the cyclohexadiene compound shown in the slide. However, careful spectroscopic analysis of the compound form allowed us to identify the formed product as the corresponding bisphenol. NMR analysis showed that our product had a CS symmetry rather than the C2B symmetry that would be expected for a conventional cyclohexadiene derivative of C60. That, by the way, we have never been able to isolate. But the most evident proof of the identity of our product was given by a much simpler observation. The bisphenol in solution had a purple color very similar to that of unreacted C60. This is a common feature of all fulleroid and bisphenol products and accounts for the maintenance of the 60-pi electron system of the original fullerene. Okay, so our question at this point of our project was, how can be a bisphenol the product of a 2+2+2 cycloaddition reaction? As I have already mentioned at the introductory part of the presentation, cyclohexadiene derivatives of C60 require photoexcitation in order to experience the sequence of events that ultimately lead to a bisphenol product. And this was not at all our case, because even when performing the reaction in the dark, the only product formed was the corresponding bisphenol. Our next question was, okay, is it possible that our rhodium complex is playing a role here? Is it possible that the reaction does not finish here as expected, but the reaction continues in order to promote the double 5-6 bond decision that leads to a bisphenol? This is something that I will try to answer at the computational part of this chapter. Okay, so with these results at hand, we proceeded to optimize the reaction conditions, and eventually we found out that using toluene binap as a ligand, working at 90 degrees at very low concentrations, and employing an excess of the diene, we managed to obtain and our desired distilled product in a 52% yield, 92% yield based on consumed C16. With this optimized set of conditions, we proceeded to analyze the scope of the reaction, and in this regard, we prepared a family of 6 sulfonamide tethered bisfluorides, in general with good yields, and also this malonate tethered bisfluoride. We also achieved further functionalization of our products. First of all, this compound readily reacted with singlet oxygen in the presence of light, delivering this dicarbonylic open cage fluorine derivatives that exhibits a 12-membered hole at the fluorine surface. This reaction could be very easily performed by simply exposing NMR samples of this product to atmospheric air and sunlight. We also prepared this iodo bisfluoride in order to allow further functionalization by cross-coping reaction. So consequently, we subjected this product to standard Suzuki-Miyaura reaction conditions with this aryl boronic acid to deliver this biphenyl bisfluoride in a 63% yield. We then applied this synthetic methodology to attach to our compounds interesting moieties from the practical point of view for the use of our compounds in organic photovoltaics. Okay, so last step in this chapter was to analyze the mechanism of the reaction. The first step of the reaction corresponds to those of the classical 2+2+2 cycloaddition reaction already discussed in chapter 3. So the rhodium complex coordinates to the 2 triple bonds of the diene. Then by an oxidative coupling, this rhoda cyclopentadiene intermediate A2 is formed. Then this intermediate coordinates to C60, and by an insertion mechanism, this rhoda bicyclopentadiene intermediate A4 is formed, and finally reductive elimination leads to this cyclopentadiene intermediate A5. But as I have already anticipated some slides ago, this mechanism does not explain the outcome of our reaction. I have also anticipated that our hypothesis is that the reaction did not finish here, but continued to finally deliver the bisfluoride. Okay, so DFT calculations confirm our hypothesis is accessible at the singlet ground state and provides a rational explanation to the formation of a bisfluoride, skipping one synthetic step that under normal circumstances would require photoexcitation. Okay, at the introductory part of the presentation, I have already explained that one of the most promising potential applications of fluorine derivatives is their use as anti-materials in next-generation photovoltaic devices. So with this idea in mind, and after we have developed our synthetic methodology and thoroughly studied the mechanisms by DFT calculations, our next objective was to assess the ability of our newly synthesized compounds, the ability of these compounds or their performance in photovoltaic devices. Okay, so in line with this, in chapter 5, I will discuss the incorporation of open cage fluorine derivatives as the electron transporting materials in perovskite solar cells. This work was done in collaboration with Professor Luis Echegoyen at the University of Texas at El Paso, and resulted after a 3-month stay in his labs a couple of years ago. Well, before I go into detail with the results, I would like to give some key ideas on perovskite solar cells, okay? So perovskite solar cells are a class of next-generation photovoltaic devices that have become very popular among the scientific community because in a very short period of time, they have reached efficiencies beyond 25% power conversion efficiency with laboratory scale devices. Moreover, they are made of earth-abundant and inexpensive materials and benefit from easy, low-cost and low-temperature manufacturing. The current challenge in perovskite-based photovoltaic devices is upscaling, which means going from these small laboratory scale devices to bigger ones with potential industrial application. However, one has to take into account that perovskite-based photovoltaics is a very young technology. In fact, the first perovskite solar cells appeared only 10 years ago. But once these issues with upscaling are addressed, for sure, perovskite solar cells are the most reliable candidates to replace currently in use and expensive silicon-based photovoltaic technology. A perovskite solar cell is constructed in many different layers. first of this layer is the photoactive or perovskite layer, which is constituted by a hybrid organic-inorganic material with the characteristic crystalline structure of a perovskite. The most commonly used perovskite material is this one here, methylammonium lead iodide. The perovskite or photoactive layer is responsible for the absorption of photons and generation of charge carriers, electrons and holes. This photoactive layer is sandwiched between an electron transporting layer and a hole transporting layer that are in turn responsible for charge extraction, charge conduction, and finally charge collection at the electrodes. Electrons are collected at the cathode and holes collected at the anode. All this sequence of events is what is ultimately responsible for the transformation of sunlight into power. Okay, perovskite solar cells can be constructed by different means and can have many different configurations. But among all possible configurations, this one, the so-called inverted planar configuration, has many advantages for commercialization because it benefits from simple device architecture, it benefits from all solution and low temperature fabrication techniques, it is compatible with flexible devices, and still inverted planar perovskite solar cells keep good efficiencies between 21% power conversion efficiency. The main disadvantage of this particular class of perovskite solar cells is that often low open circuit voltage values are obtained and consequently lower efficiencies are obtained as compared with other architectures. For the case at hand, the most important feature of inverted planar perovskite solar cells is that fluorine derivatives are used as the electron transporting layers. And in fact, fluorine derivatives are very efficient electron transporting materials because of their high electron affinity and high electron mobility, but their function is not only limited to collect and transport electrons because they also improve the stability of the devices and are able to prevent charge recombination processes by passivating the charge traps at the perovskite, at the interface of the perovskite layer. This molecule here, commonly known as PCBM, is the standard electron transporting material used in this kind of devices, but also other fluorine derivatives resulting from other reactions can be used in inverted planar perovskite solar cells. In fact, it has been demonstrated that even small changes in the chemical nature of the fluorine derivatives can dramatically improve the performance of a perovskite solar cell. So, with this idea in mind, we designed and constructed our own laboratory scale devices, but instead of using PCBM, we incorporated 3 of our open cage derivatives synthesized in chapter 4 as the electron transporting layer. We selected 3 compounds. First, this tosyl tethered open cage fluorine was used as the benchmark compound. We also selected this tripsyl tethered open cage fluorine because of the enhanced solubility provided by these 3 isopropyl moieties attached to the aryl. We chose this compound because it has been demonstrated that enhanced solubility also provides enhanced passivation ability and often results in better performance. Finally, and as a third candidate, we selected this pyrenyl tethered open cage fluorine in order to assess the influence of a light harvesting moiety at the electron transporting layer. However, this compound turned out to be completely insoluble in chlorobenzene, which is the solvent used for fabrication of the devices, which prevented us from obtaining good quality devices with this specific fluorine derivative. We also prepared some devices based on PCBM as control devices to compare the results. Okay, so first step was to analyze the HOMO-LUMO energy levels of our compounds. This was done by estimation from UV-Vis experiment and cyclical time energy experiments. And as you can see in this energy level diagram, all 3 compounds show very similar HOMO-LUMO levels to those of PCBM and showed a good match with the conduction band of the perovskite layer. This, interestingly, the tosyl tethered and tripsyl tethered open cage fluorines showed higher LUMO levels than PCBM. This was somehow an interesting result because often higher LUMO levels are related to higher open circuit voltage values and consequently better performance. Next step was to analyze the passivation ability of our compounds by performing photoluminescence experiments of the perovskite layer alone and with the perovskite layer with the electron transporting layer deposited on the top of it. This green curve corresponds to the photoluminescence intensity of the perovskite layer alone, and the idea of this experiment is to evaluate at which extent an electron transporting layer is able to quench the intensity of this photoluminescence. As you can see in the graph, the tosyl tether compound was the one that showed better, more quenching, and consequently was the one with the best passivation ability. This was somehow an unexpected result because if you remember from previous slides, we had selected the trypsyl tether compound because we anticipated better passivation ability with this specific derivative. Anyways, last step was to evaluate the performance of our compounds using this time complete devices, and we did this by recording current voltage curves, as you can see. As you can see here in these current voltage curves, the tosyl and trypsyl tether compounds were the ones that better performed. They performed better than the standard PCBM, and the best values were obtained with the tosyl tether to open-cage fluorine with a high power conversion efficiency value of 17% and a very remarkable open circuit voltage value beyond the 1 volt threshold. We rationalized these results on the basis of a better passivation ability of our compounds and higher LUMO levels which match better with the conduction band of the perovskite layer. As a conclusion, we have shown that open-cage fluorines can perform as efficient electron transporting layers in inverted planar perovskite solar cells, and moreover, we have provided a new synthetic platform to further develop other derivatives with even better performances. Okay, so I'm going to move now to the last chapter of the results and discussion part. In this chapter 6, we developed a synthetic methodology to access a series of polycyclic heterocycles starting from alkenes and 1,5-bisalines in a process that again relies in rhodium-1 catalysis. I will also explain how we applied the synthetic methodology to functionalize C60. Okay, so in previous chapters of this presentation, I have told you how we developed a synthetic methodology to access bisphenolics starting from C60 and dianes. So in an attempt to amplify the synthetic utility of our method, we wanted to apply it to other unsaturated substrates. This is why we turn our attention to 1,5-bisalines, these molecules here. In fact, 1,5-bisalines have a very rich and diversified chemistry when reacting in the presence of transition metals. This chemical diversity is clearly exemplified by these examples that I show you in the slide. So as you can see, when 1,5-bisalines are treated under catalysis with different transition metal complexes, they can deliver very diversified products exhibiting 4, 5, 6, or 7 membrane rings. For the specific case of rhodium, 1,5-bisalines can participate in 2+2+2 cyclization reactions when reacting with another alene moiety, and in 1,000-can reactions when reacting with carbon monoxide. But if you take a look at the examples that I have highlighted in these 2 slides, you will notice that most of the examples correspond to cycloisomerization reactions or homocoupling reactions in which the 1,5-bisaline reacts with itself. In fact, the only 2 examples in which a 1,5-bisaline is able to react with a third external reaction partner are these 2 ones here. This means that at the point of setting this objective, the 2+2+2 cycloaddition of 1,5-bisalines and alkenes was elusive. It had not been reported. So this is why we first wanted to develop this reaction before undertaking the more challenging, in principle, more challenging objective of fullerene functionalization. Our hypothesis was that after an oxidative coupling of the 1,5-bisaline, this would deliver 1, 2, or 3 of these rhodocyclopentane intermediates, and then insertion of the corresponding alkene, and reductive elimination will lead again to 1, 2, or 3 of these polycyclic products, A, B, or C. We wanted to direct our efforts to the synthesis of, in principle, more challenging to synthesize 7-membered rings. Once we had developed this synthesis, the ultimate step would be to functionalize furorins by using C60 as the alkene partner. Okay, so after experimenting with different reaction conditions, we eventually found out that heating a mixture of this tosyl-tethered 1,5-bisylene and ethyl acrylate in the presence of this cationic rhodium-1 complex and binap as a ligand led to the formation of this benzazepine product in a 29% yield. Remarkably, out of the 3 products that we had anticipated, only the one with a 7-membered ring, the one that we were desiring, was formed, and we also observed that the alkene had been incorporated with 100% radioselectivity. However, along with the benzazepine product, also a cycloisomerization product was formed in a 33% yield. However, carefully analyzing the structure of the product that had been formed, we noticed that it was not exactly the one that we were expecting, this one, that would form in a 2+2+2 cyclodation reaction, but a very closely related isomer with a different position of the double bond. So at this point, we set 2 hypotheses. First, an isomerization reaction that would involve a 2+2+2 cyclodation reaction and then an isomerization reaction that would lead to the isolated product, or an alternative reaction mechanism that would not involve a 2+2+2 cyclodation reaction, but would form directly this product that we actually isolated. Again, these questions were answered by mechanistic studies, but in this case we obtained both computational and experimental evidence of the mechanism of the reaction. Anyways, with these results, we proceeded to optimize the reaction conditions, and after much experimentation, we came up with an optimized set of conditions that involved the use of DTBM secthos as a ligand. So under these conditions, the desired benzazepine product was formed in a 60% yield. We also managed to get rid of the cycloisomerization product, but in turn, we obtained another one that results from 2+2 cyclodation of the internal bonds of the 1,5-bisylene. With an optimized set of conditions and in collaboration with Jordi Vila, another PhD student of our group, we proceeded to analyze the scope of the process. So we managed to apply the reaction to a series of alkyl and aryl acrylate derivatives. We also applied the reaction to vinyl ketones. We managed to synthesize these interesting tricyclic compounds by using cyclic dissociated alkenes, and we also applied the reaction to these 2 organosulfur compounds. In general, the reaction proceeded with good to excellent yields. We also managed to apply this synthetic method to this oxygen-tethered 1,5-bisylene, but in this case, as you can see here, the yields turned out to be much lower. Okay, so again, last step was to analyze the mechanism of the reaction. We did so again by DFT calculations. So our calculations made us propose the following reaction mechanism. So the rhodium complex coordinates to the 2 internal bonds, double bonds of the 1,5-bisylene, giving this intermediate A1. Then by an oxidative coupling mechanism that is selective for the 2 central bonds of the allyl moieties gives this rhoda intermediate A2 that exhibits 2 exocyclic methylene groups. Then a beta hydride elimination mechanism leads to this intermediate A3, and finally reductive elimination and substitution of the product by this 1,5-bisylene, by a new 1,5-bisylene, ultimately closes the catalytic cycle, delivering this tricyclic intermediate A5 with 2 exocyclic double bonds. This intermediate A5 readily experiences 4+2 cyclodation with the alkene, delivering the reaction product. Our DFT calculations also account for the radioselectivity of the reaction. So in this regard, the approximation that leads to the isolated product is 3 kcal per mole lower to that of the product that was never observed. As a whole, the reaction proceeds via a cycloisomerization process catalyzed by the rhodium-1 complex that forms this intermediate A5, and then this tricyclic intermediate experiences 4+2 cyclodation with the dienophile leading to the final product. So, in an attempt to obtain experimental evidence of these mechanisms, we attempted to isolate this intermediate A5. We did so by performing the reaction in the absence of the alkene. And although we did not manage to isolate this intermediate A5, we obtained indirect evidence of its formation by the isolation of this spirocyclic compound that again was formed with complete radioselectivity. This spirocyclic compound results from 4+2 cycle addition of intermediate A5 reacting with itself both as the dienophile and the diene. By the way, this compound was formed in a 58% yield. Finally, and as promised, we applied this synthetic methodology to fullerene functionalization. We did so by simply adapting the reaction conditions. This involved changing the solvent to orthodichlorobenzene and raising the temperature to 90 degrees. So with this reaction protocol, we managed to synthesize this fullerene derivative that is analogous to those obtained with simple alkenes in a 56% yield. Note, however, that in this case, a slight excess of C60 had to be used, and also short reaction times in order to avoid the formation of fullerene polyadducts. Currently, at this moment, we are analyzing the scope of the reaction with Cristina Castañeda, another PhD student of our group. This is still work in progress that we are doing now at this moment. So these are unpublished results that hopefully will be published in the near future. Okay, so these are all the results that I wanted to show. Now I'm going to finish with a set of conclusions. So in chapter 3, DFT calculations show that the 2+2+2 cycle addition reaction between C60 and two acetylenes catalyzed by Wilkinson complex is a feasible process. We also have demonstrated that the most feasible path is the one that involves oxidative coupling with two alkyne moieties. And we have also shown that the competing alkyne cyclopolymerization is favored over the reaction with C60. In chapter 4, we have demonstrated that C60 can react with a series of dienes and the rhodium-1 catalysis to deliver bispheroids in a single synthetic steps that skips the usual photochemical synthetic step. We also achieve further functionalization that can be obtained either by oxidative photocleavage and cross-coupling reactions, and we have evaluated the mechanism by DFT calculations showing that the mechanism encompasses a 2+2+2 cycle addition reaction that is followed by a rhodium-catalyzed dipymethane rearrangement and thermally allowed retro 2+2+2 cycle addition. In chapter 5, we have successfully incorporated 3 open-cage fluorine derivatives in perovskite solar cells as silicon transporting layers, and the compounds that showed appropriate solubility perform better than PCDM. High efficiencies up to 70% and high open circuit voltage values beyond the 1 volt threshold were recorded in one case. And these results were rationalized in the basis of the passivation ability of our compounds and the higher LUMO values, which allow a better match with the conduction band of the perovskite layer. Finally, in chapter 6, we have demonstrated that a series of 1,5-methylenes and alkenes can react under rhodium catalysis to deliver a series of 6-7 membered polyheterocycles. The mechanism of this reaction was evaluated, and we demonstrated that it proceeds through a rhodium catalyzed cycloisomerization reaction that delivers a 7-membered triene that experiences 4+2 cycle addition to ultimately deliver the benzodiazepine product. This synthetic methodology can be adapted to functionalize C16. As a concluding remark, I would like to highlight that all the projects that have been developed during this thesis have been developed thanks to a synergistic approach that has involved all the time the collaboration of computation and experiments. I think that this is something that represents very well the spirit of our group and the whole institute, and that has resulted very successful, in my opinion, during the development of the project of my thesis. In this case, however, 2 are not better than one because I have to ride the bicycle on my own. And this is pretty much what I had to explain today, but I cannot finish without thanking all the people and institutions that made possible my doctoral thesis. First of all, my supervisors, Professor Ana Rolans, Professor Miquel Solan, Dr. Augusto Lledó, but also Dr. Anna Pla, who has been like a fourth PhD supervisor, all current members and former members of the Metso Synthetic Lab, and very especially the students I had the opportunity to mentor because they showed high motivation and were very helpful. I want to thank very especially Professor Luis Echegoyen for hosting me in his labs and the rest of the Luis Echegoyen group. Also, all current and former colleagues of the computational chemistry labs, and of course the rest of the Linocat family and IQCC family, especially Carlos Fuertes, who will become a doctor very soon in a few weeks, hopefully. Also, the staff at the Serveis Tècnics de Recerca, the staff at the Faculty of Science, institutions for providing the money, and of course, all of you for attending my doctoral thesis in defense today. Thank you very much. Yes.
Okay, so can we go to page number 5 where we show...
Page number?
Number 5.
5, yeah.
Yeah, where you show scheme 1.2, you show the different bond types that exist in fluorines. So, yeah, could you comment on how frequently observed these different bond types are found in antique fluorines and metal fluorine? And whether are there any other fluorines that have been synthesized that have some additional forms as the one apart from the one that are shown in here?
So, how often they occur in fluorines, you mean?
Yeah.
So, well, the most common ones are type A and type D, which are the ones that you can find in C60, in C70. And sorry, and next question?
Yeah, so here you have...
There are other ones.
Right. For Christine.
To the best of my knowledge, these are the conventional ones. I don't know if other ones exist.
Okay, so yeah, there was a paper a few years ago where an X-ray structure was shown. Well, it was an metal fluorine, and this metal fluorine is an octagonal ring.
Oh yeah, a 7-member. Yeah. That's true. There is this work with a 7-member ring. So yeah, you have to consider, but this could be considered a pseudo-fluorine somehow, because the definition of a fluorine must involve hexagonal and pentagonal phases. So yeah, for the 7-membered for the fluorines that have 7-member ring, yeah, you should consider the junctions with this fluorine. Yeah, that's true.
It was like this. Okay, page 13.
13.
Yes. why are these in some cases particularly stable? Is it open adults?
Yeah, depending on the, well, for the particular case of these 2+1 reactions or carbene additions and so on, that can deliver this open 5,6 and closed 6,6 isomers, there has to be a reaction. So what you will obtain first is going to be the 5,6 open fullerene, and then this one will interconvert into the closed counterpart. So it has been shown that depending on the R groups attached to the cyclopropan ring, this process, this interconversion, is more favorable or less favorable. But well, I'm not sure of the exact reasons of this, but it has to do with the substitution pattern of the cyclopropan of the cyclopropyl ring.
But in terms of a fullerene, so having this open.
Yeah, this is for C60, for example. It has, I think it has been reported with C70 that open isomers are very stable. Yeah.
And so, but it's due to, so when you have these open adults, is there something? I mean, what property is what makes that sometimes open adults are stable?
Well, open adducts have conjugation between the carbons involved in the hole. So the sigma bond is somehow broken, but you still have conjugation. This is the reason why they have a purple color, because they maintain this conjugation between sp2 carbons. So I think the main reason why fulleroids are stable molecules is because they retain the particular filter of C60 of having 60 pi or 70 pi or any number pi electrons all conjugated. Yeah. And this is what happens with fulleroids, with these fulleroids as well. They were okay. Especially what I used to judge if the computational method I'm using is okay.
112 in the page 14.
Yeah.
So on the 110 you have the reaction working with like the simple diazole, which makes like kind of a mixture. And then on the 112, using the method, then
you obtain directly.
Yeah. Can you comment this difference?
So I have read these papers because I wanted to cover all possible transition metal promoted reactions with fullerenes, and the authors do not provide any mechanistic information on the process. They simply add this rhodium catalyst, which in general, as I assume, would form some kind of some kind of complex with the starting material, which would react selectively for 5-6 months. And they say they do not detect the open fulleroid counterpart. So I assume that it has to be something with the mechanism. And so the metal complex must modify the mechanism, so only 6-6 closed products are formed. But
it is kind of, but there was one comment that you say that indeed diazole compounds are considered unstable as all these materials, often it's often possible to isolate. Are you absolutely sure of this comment?
Sorry?
You say that is like just after the scheme 110.
Mm-hmm.
There
is
one phrase that you say that
they can be prepared.
the compound is complicated, precise, unstable, impossible to isolate it, and so on and so forth. So are you absolutely sure of this comment?
No, I base these comments on literature. I don't have experience on this.
So because these comments here can explain why you have a different selectivity in both cases.
Okay.
Because indeed diazole, there is several classes of diazole, there are some of them that are very reactive and explosive, and there's others that are not that reactive. And it's just linked to the different R1, R2 groups attached to the to this. In the first case, what happens is that because you just like cook the reaction thoroughly, you decompose diazotene from the carbene. And the carbene is very reactive. This is why probably you have these mixtures. Because then it's going to attack everything. In the second case, the diazole is a bit different. It's a bit deactivated, okay, with a weathering group. When you put the metal, then you do a metal carbene chemistry. And then the reactivity is completely different.
This is what I meant.
But with the metal carbene chemistry, the carbene is less reactive. And so it's more selective. And this is the difference between the two cases. And if, for example, you have an extra weathering group instead of a hydrogen on the scheme 112, this diazole is very stable. And it's that
I després per les posicions m'ha semblat que s'ha dit. Jo crec que aquestes diapositives es devien veure molt bé des de la part de l'any.
Molt.
I això és d'agrair perquè no sempre passa.
Exacte.
Suposo que has tingut també bons consells. I volia fer extensiva la felicitació als teus supervisors de tesi pel seu treball de direcció. Algunes de les preguntes, o moltes d'elles, ja han sortit perquè s'ha discutit realment a bastament. Per tant, per dir més breus, potser hi ha coses més generals perquè no cal tornar a incidir en moltes algunes. In the group, they have some experience, or a wide experience in the cycle addition reaction with volume, and also in the calculations with chemistry. But you have been the first one to work experimentally with this type of compound. So I would like to comment a little bit on that. The fluorine derivatives have some peculiarities or some difficulties with respect to the manipulation or with respect to the characterization. If you compare with the other kinds of substrates we mentioned that we used in the group in the past, or comment a little bit on that. How about the experimental details about this type of
the daily work with this one. Yeah, it might seem frightening at the beginning, changing from conventional organic chemistry to carbon nanostructures, but C60 and other fluorines, but mainly C60 has the particularity of being the fluorine that is behaves very similar to conventional organic reagents. And in fact, unlike other carbon nanostructures, fluorines are discrete molecules, so they behave more or less similarly to simple alkenes. Okay, but they have also advantages and disadvantages. For example, one good advantage that I was really happy to observe the first days working with fluorines is that you don't need TLC.
Recordeu que el cum laude no es dona, la menció cum laude no es dona en aquesta sessió, sinó que se'ns publicarà més tard per part de l'Escola de Doctorats. Bé, et voldria felicitar per vegada més, ja que ho hem fet al principi, que volia fer-ho ara, per tot el treball realitzat, per l'exposició que has fet i per la defensa, i desitjar-te molts èxits en el futur. Que et veiem l'altra vegada fent una conferència o així. Full professor.